Okay, so I would like to conclude the discussion concerning the permittivity of the metal in the Drude model. So last time we saw that the relative dielectric constant has a frequency dependence that is described by this function. So the permittivity as a function of omega is equal to 1 minus the ratio between the square of the plasma frequency and the square of the frequency of the external perturbation. And again, as I described during the last lesson, here you have just a dependence on the frequency and not on the wave vector. So we do not expect any position dependence of this dielectric constant due to the fact that if we want to discuss the properties of the metal in the visible light range, in that range of frequencies, the wavelength of the external perturbation is very, very large with respect to the mean free path of the electron. So the electron is not able to detect the position dependence of the external perturbation. Due to that, just the frequency here is included. If we make a plot of the relative permittivity as a function of the frequency, what we observe is that the permittivity goes to 0 when the frequency of the external perturbation is equal to the plasma frequency. So here we have the dependence goes to 0. Then when you send omega, the frequency of the external perturbation to infinity, what you have is that epsilon is equal to 1. So we have that the value of the permittivity is nearly 1 when the frequency is very large. And then if you send the frequency to 0, you have a divergency. So the permittivity goes to minus infinity. So at the end, the dependence is like this. So what we have is that a change of sign is observed. So for omega larger than the plasma frequency, we have that the permittivity is larger than 0. If the frequency is smaller than a plasma frequency, then the permittivity is negative, so it's smaller than 0. So what is the effect of that? When the permittivity is larger than 0, we have that the index of refraction, that is the square root of the relative permittivity, just a comment concerning this sentence. In principle, the index of refraction is not just the square root of the relative permittivity, it's square root of the permittivity of the medium times the magnetic permeability of the medium. But in this case, I assume that the magnetic permeability is equal to mu0, so just vacuum. And the relative and the permittivity of the medium is epsilon of omega times, so the total permittivity is E0 times epsilon of omega. So at the end, E0 is a positive constant. So at the end, the sign of the of what you find within the square root of when you evaluate the index of refraction, so n should be E total. In this case, it's just E total times mu0 because there's no, again, the Drude metal has no magnetic properties. So the sign of what is here within the parentheses is just due to the relative permittivity, because all the other terms do not change sign depending on the frequency or on other terms. So in this case, the sign of what we have here within the parentheses is equal to the sign of the relative permittivity. So for omega larger than plasma frequency, we have that the index of refraction is real. If that is real, this means that you may have propagation of the external perturbation within the metal. You may have something like, I don't know, light that goes from air to glass, air to water, so air to a transparent medium. So you may have some changes, but at the end the wave is able to propagate through the metal. So the metal is transparent in that range of frequencies. If omega is smaller than omega p, n is complex. So you may have transmission, but you have also absorption. So this means that the light is not able to go through the medium and, let's say, go into the medium from one side and go out of the medium on the other side. So in this case, you have what we usually know about metals. That is, metal is not able to transmit light, but just to reflect light. So in this case, this is what you expect from a metal. So from a metal, you expect absorption. You don't expect transmission. And to understand why is it possible to say why this behavior is actually in agreement with what is found experimentally, the important thing is to evaluate omega p, just to understand what is the when this transition from transparency to absorption takes place depending on omega p. Just because maybe one is more used to distinguish the electromagnetic waves not in base of the frequency but just in base of the wavelength, I just try to evaluate not omega p but the wavelength corresponding to omega p. So if omega p is 2 pi, let's say the frequency corresponding to omega, if we write that as c divided by lambda p, then in this way, and this is the square root of the value of the plasma frequency. So in this way, we may evaluate, for instance, lambda p. So lambda p is 2 pi times c m is 0 divided by n e squared to the power of 1/2. So in this case, if c, the speed of light, we use 3 times 10 to the 8 meters per second. And if we make the calculation for aluminum, so in the case of aluminum, the electronic density is 18.1 times 10 to the 28 electrons per cubic meter. And yeah, the mass of the electron is always 9.1 times 10 to the minus 31 kilograms. And then if we use E0, make the square root, what we find is that lambda p is equal to 397 nanometers. 397 nanometers means close to the UV range of the spectrum. So what is found is that the plasma frequency, or in this case, the plasma wavelength, is a wavelength that is not in the middle of the visible range of light, where our eye is more sensitive, but is close to the UV side of this spectrum. And this happens for all the metals. So the exact value of the plasma wavelength changes depending from metal to metal, due to the fact that the electronic density changes from metal to metal. But then in general, you find that that frequency or that wavelength is in the UV range. So the fact that that wavelength is in the UV range explains why when you look at the metal, you do not observe that the light is able to go through the metal, because our eye is not so sensitive in the UV range of the visible spectrum. So we are not able to detect directly with the eye the fact that the metal is transparent in that range of frequencies, because we see all the visible part of the spectrum that is not strictly in the UV range. So we see the main effect from all the wavelength in the visible range, that is absorption, not transparency. But if you make an experiment, you take a source of electromagnetic waves, and you make a plot where you make the you plot on the horizontal axis the wavelength, and on the vertical axis the transmission, then if you have full transmission, then T is equal to 1. If you have a full absorption, that T is equal to 0. So what is observed is that close to lambda P, you have a transition from 1 to 0. So you have this transition from the typical metallic behavior that we observe in the visible light range and what is actually predicted from this model. So as a general comment, due to the fact that this behavior was observed, was actually observed for the metals, this was a confirmation of the fact that the Drude model was fine, or was at least in agreement with the experimental observation. The only problem, if we may call that a problem, is that from the point of view of the optical properties of the material, the only free parameter that you have here is the electronic density. And if the only parameter that you have at disposal to switch from, let's say, one metal to another metal is the electronic density, this means that the only parameter that will change within the model is the value of the plasma frequency or the plasma wavelength. So the only free, let's say, free parameter that distinguishes one metal from another metal is lambda P or omega P, depending on what is the parameter that you prefer to use. So with this model, you are able to, let's say, describe a typical metal that is something that behaves like aluminum, silver, or alkali metal. So something that is bright and reflect light. So that is the typical metal that can be described with this model. But changing only the lambda P parameter or the omega P parameter, you are not able to describe something like gold or copper, because gold and copper have a color. So they are bright, they reflect light, but they also have a color. Using this model, you are not able to predict a color, any color, because the only, let's say, change of the optical properties that you may have here is the change of a parameter that is lambda P or omega P that are in general in the UV light range. So as that parameter will never enter the visible light range, you are not expected to be able to change that much the optical properties of a metal described with the Drude model. So in general, the model is fine. The question mark is what about the color of, for instance, copper or gold? Because that is expected to be due to something that is slightly more complicated than just a free electron metal. But let's say I pointed out that, but in general, let's say the average metallic behavior is fully described by this approach. So again, the question mark is just due to the details. So not the main behavior, but the details, in particular the color. So please keep in mind the fact that using just a free electron picture where the electrodes are considered to be classical particles is not enough to describe all the details of the optical properties of this system. And Just one comment concerning the frequency or the wavelength. Why plasma? So why do we call that plasma frequency or plasma wavelength? In general, if you have a system where you have electrons, as in this case, and you consider the electronic density, in general, the electronic density will not be strictly uniform. So you may have oscillations, perturbation of the electronic density. And in general, a perturbation of the electronic density is called the plasmon. So a plasmon is, let's say, an excitation of the electronic density that is no more uniform, but displays some deviations from being uniform. In particular, so plasma means the electronic density is oscillating, is changing in some way. Let's see what happens if we consider this concept of oscillation of the electronic density to the case of the Drude metal. In the case of the Drude metal, if we consider this box to be the metal, and if we suppose that the length of the metal is L, and the surface area of this box is equal to S. So we have this box S time with a volume equal to S times L. Now let's suppose that in principle this box is made by a positive background of charge that is due to the ions and a negative background of charge that is due to the electrons, and the electrons, due to the attraction between positive and negative charges, are forced to stay, let's say, within the box. It may happen that you may have a short displacement of the electronic charge of all the electrons. And just to make the calculation simple, I suppose that the displacement is just in the horizontal direction. So let's suppose that if we take as a reference the horizontal axis, let's say the electronic charge is not exactly over the shape of this box of this solid, but is displays a slight translation. So let's suppose that we have this translation of the electronic charge density to the right. What happens now due to this translation? In this case, we have that the left side of the solid becomes positively charged due to the fact that you miss you have no electrons, let's say, on the left side of the solid. So in this case, we have an accumulation of positive charges. On the other side, on the right side, we have an accumulation of negative charges because the electrons are slightly out of the box, let's say, on the other side. So in this case, we have a negative charge density. So what happens here is that the solid has become a capacitor because you have two slabs parallel with each other. On one side, negative charges, on the other side, positive charges, and the amount of charge that you have on the two slabs is exactly the same. So in this case, we have an electric field, and the electric field is from the left to the right. So the external field is like this. And if the external field is like that, then the electrons are forced to go back to the initial position because that field forces the electrons to go back to the initial, let's say, configuration where you have electronic charges exactly over the negative charges exactly over the positive charges. So you have that any oscillation produces a restoring force that tries to bring the system back to the equilibrium. In this way, we may write down the equation of motion of this system using the second law of dynamics. So we may write that the force applied to the electronic cloud is equal to mass of the electronic cloud times the acceleration of the cloud. In this case, what is the mass of this cloud of electrons? The mass is the mass of all the electrons that you have in the box. So the mass is equal to the volume of the box times the electronic density times the mass of one electron. Just to distinguish mass of the system from mass of the electron, I write as a label E for the mass of the electron. The acceleration, since here we're supposed to have a motion that is only along the x direction, I may write, I may suppose that I have an equation, a function x of t that describes the center of mass, let's say, of the electronic cloud that is oscillating. So the acceleration in this case is only ax, the component of the acceleration along the x direction. And that may be the second derivative of x of t, where x of t is the equation that at the moment we do not know, that describes the position of the electronic cloud. Force. The force is a restoring force that depends on the electric field within the capacitor. And the force is, in this case, Q total, that is the total charge of the electronic cloud, times, I just write, let's say, I just write Fx, because I have force only along the x direction. So that is equal to total charge, then times the electric field that I have along the x direction. And then when I write down the equation, I will include the minus sign that is the indication of the restoring force that we have here that brings the system back to equilibrium. So if we write the equation of motion for this system, yeah. So we have that the total mass S times L times electronic density, mass of the electron, times the second derivative of x is equal to the Q total. Q total is the charge of one electron times the number of electrons. And the number of electrons is S times L times the electronic density. So this is Q total, and here we have the minus sign due to the charge. Then the electric field. The electric field is the electric field produced by a capacitor. And the electric field of a capacitor is the ratio between the charge density at the positive slab divided by E0, because here we use again E0 as we were in vacuum. The density charge at the positive slab is equal to the thickness. I just make again the picture here. So if we have a translation of the electronic cloud, the thickness of the slab is equal to the amount of the displacement. So if the displacement of the electronic cloud is x, the thickness of the slab is also equal to x. So this thickness here is x, because if the translation of the cloud is equal to x, then x is equal to the thickness of the positive and also of the negative slab. So in this case, Ex is equal to, sorry for the fact that the charge density is exactly the same symbol of the conductivity. So please, this is a surface charge density is sigma divided by E0 So we have 1 divided by E0 times the amount of charge that we have in that small thickness, and the amount of charge is equal to S times X, that is the volume of the slab, times the electronic density of the electrons, times E, because when you consider a capacitor, you only consider the positive charge density to evaluate the field's potential and so on. So this is the amount of charge that we have within that slab. To have the charge density, we have to divide by the surface of that slab. So that this is the charge, surface charge density. So if we now combine everything within just one equation, we have the acceleration, let's say, that is equal to minus E S times L times N, times the electric field, that is 1 divided by E0 X times N times E. Okay. So at this point, we may simplify SLN that we have on both sides. So SLN, SLN. We may also take the electronic mass to the right side. So I also divide by ME. So the final equation is that the second derivative of X is equal to minus N E squared divided by electronic mass E0 times X. And this is the equation of an oscillation that takes place with the frequency equal to the square root of that. So in this case, the frequency of this oscillation that you expect to observe is equal to NE squared divided by ME0, all to the power of 1/2. So the plasma frequency represents the frequency of oscillation of the motion of this cloud of electrons due to the restoring force that is activated when you consider the fact that, again, any oscillation of the electronic cloud in this way, like the one that I described to you, produces a surface charge that tries to bring the electronic cloud back to the equilibrium position, where the center of mass of the electronic charge is equal to the center of mass of the positive charge. Yeah. Just a small comment, and I will go back on that in a few weeks when we will discuss the same phenomenon in using another model. I told you at the beginning that in general, plasma oscillation is an oscillation of the electronic density. So the electronic density is not uniform, but have some distortions. And the oscillations that are produced due to those distortions are called the plasma oscillations. In this case, what I described to you is not actually an oscillation of the electronic density, because here it seems that all the electrons in a rigid way oscillate back and forth over the positive background of charge. So this is a sort of rigid oscillation of all the electronic cloud. In principle, if this oscillation takes place, this means that this is, let's say, just a rough way to describe it. If you're supposed to be the, let's say, first electron on the left, and the first electron on the right oscillates exactly following your equation of motion, then this means that instantaneously the motion of the first electron on the left influences the motion of the first electron on the right. So you should have an instantaneous transmission of the information from the left side to the right side of the box, irrespective of the size of the box. So this means that in principle, to suppose that this rigid oscillation takes place, means a sort of violation of the fact that the information may not be instantaneously transmitted from one side to the other side of the box. So this means that we are assuming that C is equal to infinite, because instantaneously all the electrons know what all the other electrons are doing during the motion. As we will see later, when we consider the fact that C is not infinite within the model, we will observe that actually what we observe is not a rigid oscillation, but it's just a modulation of the density charge. So in one point, you have, let's say, a decrease of the density. In another point, you have an increase of the density. So you have a density that from point to point changes depending on what is the electronic system doing. And in that case, this behavior will be in agreement with the fact that C is not infinite, but has a finite value. So for the moment, I didn't describe just a general perturbation, but it's only a specific perturbation. And this specific perturbation, please keep in mind that is just a way to describe the phenomenon, the oscillation, and to obtain a value of the frequency that is exactly equal to the plasma frequency that we obtain from the calculation. But within this picture, we are somehow assuming that again C is infinite, and this is not the case. So there is just this small detail to consider when we discuss this simple picture to give a meaning, let's say, to the value of the plasma frequency that was obtained from the Drude model. Okay. Regarding this part, that was the calculation, let's say, of the relative permittivity of the system, plus this short discussion of the optical properties. Do you have some questions or comments? Yeah. See? Yeah. Yeah, from the electric. Yeah. Just from the fact that the electric field in this case induces a restoring force due to the fact that the charge of the electrons is negative. So that brings back the electrons tries to bring back the electron to the initial position. Okay. Before, let's say, concluding the discussion of the Drude model, I would like to include just an additional a very short calculation concerning another property of the system described by the Drude picture. And the last point I would like to discuss with you is the one concerning the evaluation of the specific heat of the metal. I would like to discuss also this point due to the fact that specific heat, optical properties, conductivity will be the topics that I will always discuss irrespective of the model we have I'm presenting to you. So I will always try to discuss how conductivity changes depending on the model we use, how optical properties change depending on the model, and how also the specific heat changes depending on the model we use to describe the properties, the microscopic properties of the system. The last step here is the evaluation now. Why is that important? Because, let's say, the specific heat, the dependence of the specific heat on temperature, and also the value of the specific heat were known because they were measured. So what they knew is that if you plot the specific heat as a function of the temperature, what you observe is that At high temperature, you have more or less a dependence that is nearly constant. So here you have something that is very close to a constant value. And then at low temperature, the specific heat goes to 0. And close to the range of temperature where T is close to 0, you have a polynomial dependence that can change from proportional to T to the power of 3. In any case, you have something polynomial. And then the dependence changes, and you approach the constant value that you have at high temperature. So, so in this case, the idea is it possible to describe this experimental dependence using the hypothesis of the model? So what Drude tried to do was to evaluate the specific heat considering the system he was handling. In this case, the system is a solid, a metallic solid. And if we just recall the definition of specific heat, the specific heat is the derivative with respect to the temperature of the energy density of the system. So the ratio between the total energy of the system and the volume of the system itself. In this case, in the case of the Drude model, what contributes to the total energy of the system? The metallic solid includes ions and electrons, but ions are fixed in their positions. They do not change their position. They do not exchange energy with the environment. They are just there to provide the charge neutrality of the solid. So ions, let's say, participate to the formation of the solid, but are not able to exchange energy with anything. So ions are there, but do not contribute to the value of U, because here we do not consider, for instance, the potential energy due to the fact that we have positive charges and negative charges. We just consider that the electrons are independent and free, so no interaction with the ions. So the ions do not contribute to so the ions do not contribute to the value of U. The only thing that may contribute here to the value of U are the electrons. So only the electrons can participate and contribute to the total energy of the system. How do the electrons contribute to the total energy? We know that the picture that Drude used was the one where the electrons are classical particles that are described by the Maxwell-Boltzmann distribution, and the average energy per electron depends on the temperature. So the average value of the average energy per electron is proportional to T, to the temperature. And in this case, we have 3 divided by 2 times Kb times T. So this is the only contribution. Due to that, if you write down U, that is the total energy, due to the fact that the energy does not change from electron to electron, but is always the same. So you may just write number of electrons times 3 divided by 2 times Boltzmann constant times temperature. So when we, at this point, try to evaluate the specific heat, we have the derivative with respect to temperature of the energy density. We have to divide by the volume. So number of electrons divided by the volume is the electronic density. So this is the electronic density times 3 divided by 2 times Kb times the temperature. So if we make the derivative, this is just 3 divided by 2 electronic density, Boltzmann constant. And the first thing we note is that you have no temperature dependence. So due to that, we for sure miss to properly describe the experimental data, because there you have a temperature dependence. And just to rewrite this expression in a way that is more familiar, let's say, we may write the electronic density as the product of the molar density, so number of moles per unit volume, times the Avogadro number. So we may write that as 3 divided by 2 times the molar density, so moles of electron per unit volume, times the Avogadro number, times Kb. The product of the Avogadro number times Kb is the constant of gases, R. So this is 3 divided by 2 times the molar density times the constant of gases. The constant value here that was measured and determined experimentally is 3 times molar density times constant of gases. So we may say that the constant value that is at the end known as the Dulong and Petit law. So the Dulong and Petit law tells us that the specific heat in the temperature independent regime is equal to 3 times constant of gases times the molar density of the solid we consider. In this case, the electronic contribution is just 1/2 of that, because it's 3 divided by 2 times the molar density times the constant of gases. So the electronic contribution is 1/2 of the experimental value and the expected value. So in this case, we miss 2 things. One thing is the temperature dependence. The other thing is the value, because other models, and we will see that those models in the next weeks, are able to predict the let's say, the Dulong and Petit value, that is the asymptotic value that you observe at high temperature, but miss the temperature dependence. In this case, again, we also miss the absolute value of the specific heat. And let's say, just to make a short comment on that, the problem here is due to the fact that on one side, we are considering electrons using a classical distribution. So this is one of the problems. The other problem, that is the main one, is the fact that we completely neglect the ions. So the fact that we here do not consider any contribution coming from the ions in the solid is the main source of the failure of this prediction. We will see that when the contribution coming from the ions will be considered, then we will be able to fully describe all the dependence of the specific heat on the temperature. So in this case, that is the main point. Along with the fact that, again, we are discussing electrons as if they were classical particles. Okay, so this is the last topic I wanted to show you concerning the Drude model. And if for you it's fine, now I would just make a short summary of the model, not all the calculations, just the main points, just to fix everything, to have everything at disposal, and to understand what is next. So what is the next step of approximation when we try to describe the properties of a metal, trying to include the, let's say, new contributions that were observed at the beginning of the previous century. Because when Drude presented the model, nothing concerning quantum mechanics was known. But in the first 25 years of the previous century, then we switched from the classical world to the quantum mechanical one. So a lot of novelties appeared, and those novelties were then used for the description of the solid state. Just to summarize the main hypothesis of the model and the details that were obtained by the model. So the Drude model was the the Drude model was based on the fact that the electrons are free and independent. Both hypotheses were not demonstrated, were not justified. So there is not a motivation that I may give you at this moment to justify the fact that the electrons can be considered free. So the fact that they do not interact with the ions, and independent, that means they do not interact with each other. So for the moment, we just use those hypotheses, but those hypotheses are not are not discussed. And they just come from the fact that Drude tried to apply the model of the ideal gas to the case of electrons. So Drude just removed the opportunity that the electrons may collide with each other as the ions, as the molecules in a gas, and replaced this kind of interaction with the collisions. So in the case of the model, we have this interaction between the electrons and, according to this model, the ions, and the contribute of collisions is at the end on one side to produce resistivity, or to produce a conductivity that is not infinite, because otherwise, if you remove collisions, then nothing may prevent an electron from moving from one side of the box to the other side in a straight, according to following a straight line, and so having a ideal infinite conductivity. So collisions introduce resistivity, but the main point is the fact that collisions are a way to take the system at the equilibrium, to bring the system back to equilibrium. So to prevent, for instance, an electric field to transfer energy to the electrons without an upper boundary. So thanks to collisions, this transfer of energy between the external field and the electron may not take place for an infinite time, but takes place only for a time that is at most equal to the relaxation time. So collisions and their relaxation time are a source of resistivity and are a mechanism that bring the system back to equilibrium. So this kind of interaction is the interaction that produces let's say, a sort of restoring force that prevents the electronic system to deviate very much from the equilibrium, where equilibrium means the Maxwell-Boltzmann distribution. So what we know is that that distribution describes the properties of the electrons. So the energy, the velocity of the electrons is described by the Maxwell-Boltzmann distribution. So the average energy per electron is proportional to the temperature. Okay, so starting from those hypotheses, what we evaluated the conductivity the whole coefficient that is important, as the Hall coefficient does not depend on the relaxation time, but allows us to evaluate the electronic density. And thanks to the value of the electronic density, we may also use, for instance, the conductivity to evaluate the relaxation time. So somehow we may have a comparison between the, let's say, initial values of, for instance, the electronic density, as the electronic density was initially set to be proportional to the number of electrons that are shared with the solid to form the metallic bonding. So we may have a confirmation, for instance, of the value that we use for ZA, or we may modify that value if that value gives us an electronic density that is very far from the value predicted, no, sorry, not predicted, by measured through the Hall effect. So the Hall effect is a sort of check of the value of the electronic density that we may inject into the system. We also observed, we also try to describe the frequency dependence of the conductivity that gave us the opportunity to evaluate the permittivity of the system that is related to the optical properties. And what we saw is that the optical properties are the optical properties of the average metal, so reflection, bright behavior, but we still miss some details concerning, in particular, those concerning the fact that some metals may have a color that is not just the typical bright color that you observe for metals, as for instance aluminum or silver. And then the final step was the specific heat that was 1/2 of the value predicted by the Dulong MPT law, so smaller than that expected. Also, in the case where when we have a specific heat that is not dependent on temperature. So we have some points that are in favor of what is are in agreement with what is experimentally found, and also some points that are not in agreement with that. So anyway, this is the first model, so it may happen that something agrees with reality, with the actual metals, and something not. And what I would like just to include is the fact that, in general, if you want to investigate a system, you do not start with the more complex model you have at disposal, because as a first step, you try to use the simplest model you have at disposal to try to compare the properties of that model to the properties of the system you want to investigate. And why you do that? Because at the first step, you maybe do not know all the details of the system you have in front of you. So at the beginning, you try to compare with the properties of that just the simplest picture, so to understand where your system deviates from this picture and where your system is in agreement with this picture. Now, for the moment, this sentence is maybe not the full meaning, because we are just at the beginning of the lessons, but later on we will understand why this comparison can be important, because in some cases, even the most complicated models tells you exactly what the Drude models predicts. So there are situations where even more complicated models tells you exactly the things that the Drude model predicts using this simple approach. Another thing that, let's say, maybe in favor of the use of the Drude model just for a simple first approach to the material you want to investigate, is the fact that we may consider all the quantities of the Drude model as effective quantities. What is the meaning of effective? For instance, the conductivity is n e squared tau divided by the mass, where m is the electronic mass, the electronic rest mass, and n is the density that comes from the evaluation of ZA. But for instance, let's say you may evaluate n using the Hall coefficient. So you may have the, let's say, actual value of n. At this point, you may, for instance, notice that even if you use the actual value of n, the conductivity is far away from the experimental value. So at this point, you may decide to use m as a parameter, not as the value of the electronic rest mass. So you may decide to define an effective electron mass such that if you use in the equation the effective electron mass, the equation predicts values that are in agreement with the experimental result. What is the meaning of that? The meaning of that is, on one side, if you want to use this simple picture to describe a complex system, maybe you have to tune the picture to be in agreement with the complex system. So you may use as tuning parameters both the electronic density that you may evaluate, for instance, through the Hall coefficient, and the electronic mass. So in this case, what I call here m star is not, let's say, if I find a value that is 4 times the electronic rest mass, this doesn't mean that in my system I have electrons whose weight is larger than normal electrons. So this is not a physical conclusion. But it's just that in my system, if I want to use the Drude picture, that is a simple one, to be in agreement, to find results that are in agreement with the actual results, then I may rescale the electron mass. And what I noticed is that, for instance, if the electron mass is 4 times higher than the rest mass, then everything is fine. So for the moment, this is just a sort of artificial tuning, because no one may justify me the fact that why should I use a mass that is 4 times larger than the electronic rest mass? So for the moment, this is just a trick, let's say. I just anticipate you that when we will consider the effect of the ions on the motion of the electron, we will actually find that the inertia of the electron changes, because electron is not moving through vacuum, is moving through positive charges, and the positive charges attract the electron. So your capability to move the electron, that somehow is the way you may use to, let's say, sense the mass of the electron, may give you a response, so a value of the mass that is actually different from the rest mass. Due to the fact that I'm not, let's say, my English is not so good, so maybe I'm not able to express complicated concepts in English as I would do in Italian. Do you mind, also, I also make this question to the guys that are connected online, do you mind if I try to repeat all I've just said in Italian?
No, it's fine, you can't.
Ok, quindi l'idea è questa. Il modello di Drude è molto semplice, quindi non possiamo pretendere che riesca a cogliere tutte le finezze e i dettagli dei sistemi più complessi. Quindi quello che posso fare è spesso usarlo come modello fenomenologico. Quindi dire, il modello mi dà queste previsioni sulla base del valore della massa a riposo dell'elettrone, della densità elettronica, che sono gli unici parametri che ho per accordare le previsioni del modello al sistema. Non ho altri parametri liberi, quello è solo quello. Quindi per cercare di adattare un sistema così semplice a, di nuovo, materiali che sono ben più complessi di questo, quello che posso fare è rilassare un attimo le condizioni e dire, ok, se uso la densità elettronica che troverei con ZA e la massa a riposo dell'elettrone, trovo dei dati che non sono per niente in accordo col dato sperimentale. Ma se considero quei parametri come parametri liberi, che mi servono per adattare il modello a quello che vedo, allora a questo punto la densità può cambiare e anche la massa a riposo dell'elettrone può cambiare, fermo restando che in mente non mi devo immaginare un elettrone più pesante che gira nel metallo, ma mi devo semplicemente immaginare M asterisco come una massa efficace che fa tornare le cose, nulla di più. A questo punto voi potreste chiedermi perché mai devo inventarmi queste cose per non usare un modello più complesso. Uno, perché alle volte usare un modello più complesso potrebbe richiedervi molto tempo per vedere una conclusione. Quindi è meglio capire dall'inizio quali sono i problemi che ha il modello più semplice per riuscire a capire se il modello più complesso vi può dare una mano. E questo di nuovo lo vedremo dopo quando avremo a che fare con modelli più complessi. Un altro aspetto è il seguente, ovvero nel momento in cui terremo conto del fatto che l'elettrone si muove in un reticolo, l'elettrone interagirà con quel reticolo. Quale sarà uno dei risultati di quell'interazione? Uno dei risultati sarà che non muovendosi nel vuoto, ma muovendosi in mezzo ad un sistema periodico di cariche positive, le cariche positive attirano l'elettrone. Quindi l'elettrone, applicando una forza esterna, reagirà in modo diverso da come avrebbe reagito se fosse stato in vuoto. A questo punto cosa veniamo noi dall'esterno? Applico un campo, l'elettrone non accelera come se fosse nel vuoto, ma accelera in maniera diversa, è come se avesse cambiato la massa. Volendo, prendete con le pinze questa frase. Quindi il fatto di usare delle masse efficaci non è un mero artificio, così un giochino, un trucco magico che fa tornare le cose, ma è un modo per introdurre in questo sistema, che è veramente il più semplice di tutti, il concetto, l'idea che l'elettrone quando si muove non è nel vuoto, ma interagisce con tutti coloro che gli stanno attorno, quindi con tutti gli altri elettroni e con gli ioni del reticolo. Questa interazione può cambiare la risposta dell'elettrone ai campi esterni. Quindi ammettere l'uso di una massa efficace in questo contesto è come ammettere che non siamo capaci di gestire la complessità del sistema, ma cerchiamo di farla rientrare definendo delle quantità efficaci. Quindi di nuovo, questo non ve la sto proponendo come filosofia di vita, cioè solo il modello di Drude e mai più nient'altro, ma semplicemente come un primo approccio ad un sistema per capire cosa va e cosa non va, così da indirizzare lo studio successivo fatto con mezzi più complessi e che tengono sicuramente conto dei dettagli del sistema che vi troverete davanti un domani. Quindi in questo contesto il modello può avere una sua utilità. Domanda. Io oggi non ho 2 ore, un po' di più, quindi per voi va bene se io interrompo adesso col fatto che ho chiuso un argomento e poi la restante parte della lezione la dedico a presentarvi e andare avanti con l'argomento nuovo. Quindi se voi va bene, io interromperei adesso. Può andare bene? Is that fine also for the guys that are connected?
Va bene.
Sì. Ok, so ok, facciamo una piccola pausa e poi riprendiamo con il resto della lezione.